Hello, welcome to the final section, Advanced Continuous Delivery. In this section, we will first explain how to approach database changes in the context of continuous delivery and introducing the idea of database migration and related tools. Moving on, we will be exploring different approaches to backward-compatible and backward-incompatible database updates. Then we will be using parallel steps in the Jenkins pipeline and creating a Jenkins shared library. Finally, we will be introducing continuous delivery for legacy systems. Now we move on to the first video of this section, Managing Database Changes. In this video, we are going to first understand schema updates and then using Flyweight and finally changing the database. Database schema migration is a process of incremental changes to the relational database structure. Let's have a look at the following diagram to understand it better. The database in the version v1 has the schema defined by the v1_init.sql file. Additionally, it stores the metadata related to the migration process. For example, its current schema version and the migration changelog. When we want to update the schema, we provided the changes in the form of an SQL file, such as v2_add_table.sql. Then we need to run the migration tool that executes the given SQL file on the database. It also updates the metatables. In effect, the database schema is the result of all subsequently executed SQL migration scripts. Next, we will see an example of a migration. Migration tools and the strategies they use can be divided into two categories, upgrade and downgrade, upgrade only. Let's use Flyweight to create a database schema for the Calculator web service. We show how to use the SQL database and Flyweight in 3 steps. The first step is configuring Flyweight. In order to use Flyweight together with Gradle, we need to add this content to the build.gradle file. We use the H2 database, which is an in-memory database. We store the database in a calculator file. The default database user is called SA. After this configuration is applied, we should be able to run the Flyweight tool by executing this command. The command created the database in the file /tmp/calculator.mv.db. Obviously, it has no schema since we haven't defined anything yet. The next step is to define the SQL file that adds the calculation table into the database schema. Inside migration folder, we create a v1create_calculation_table.sql file with this content. Note the migration file naming convention. The SQL file creates a table with 4 columns, ID, A, B, result. The ID column is an automatically incremented primary key of the table. Save this. Now we are ready to apply the migration. For this, we run the Flyweight command. As you can see, the command has automatically detected the migration file and executed it on the database. We executed our first migration, so the database is prepared. To see the complete example, we should also adapt our project so that it would access the database. Let's first configure the Gradle dependencies to use the H2 database from the Spring Boot project. To do this, open the build.gradle file and add this code. The next step is to set up the database location and the startup behavior in the application.properties file. The second line means that Spring Boot will not try to automatically generate the database schema from the source code model. On the contrary, it will only validate if the database schema is consistent with the Java model. Now let's create the Java ORM entity model for the calculation in the new calculation.java file. Here we have added this code. The entity class represents the database mapping in the Java code. A table is expressed as a class and each column as a field. The next step is to create the repository for loading and storing the calculation entities. For this, we create the calculation repository.java file, and it contains this code. Finally, we can use the calculation and calculation repository classes to store the calculation history. So in calculatorcontrol.java file, we have added this code. Now when we start the service and execute the /sum endpoint, each summing operation is logged into the database. If you would like to browse the database content, then you can add spring.h2.console.enabled equals true to the application.properties file, and then browse to the database via the /h2-console endpoint. We explained how the database schema migration works and how to use it inside a Spring project built with Gradle. Now let's have a look at how it integrates with the continuous delivery process. The first approach to use database updates inside the continuous delivery pipeline could be to add a stage within the migration command execution. This simple solution would work correctly for many cases. However, it has two significant drawbacks: rollback and downtime. This leads us to two constraints that we will need to address. The database version needs to be compatible with the service version all the time. The database schema migration is not reversible. We will address these constraints for two different cases: backward compatible updates and non-backward compatible updates. Backwards compatible changes are simpler. Let's look at the following figure to see how they work. Suppose the schema migration database v10 is backward compatible. If we need to roll back the service v1.2.8 release, then we deploy service v1.2.7, and there is no need to do anything with the database. Database migrations are not reversible, so we keep database v11. Since the schema update is backwards compatible, service v.1.2.7 works perfectly fine with database v11. The same applies if we need to roll back the service to v1.2.6 and so on. So, suppose database v10 and all other migrations are backward compatible, then we could roll back to any service version and everything would work correctly. Let's look at an example of a backward compatible change. We will create a schema update that adds a created@* column to the calculation table. For this, we have created v2_add created@* column.sql file, and it has this code. Besides the migration script, the calculator service requires a new field in the calculation class, so save it and go to calculation class and add this line. After running the service, the calculation history is stored together with the created@* column. Note that the change is backward compatible because even if we revert to Java code and leave the created@ column in the database, everything would work perfectly fine. Non-backwards compatible changes. Non-backwards compatible changes are way more difficult. Looking at the previous figure, if database change v11 was backward incompatible, it would be impossible to roll back the service to 1.2.7. In this case, how can we approach non-backward compatible database migrations so that rollbacks and zero downtime deployments would be possible? To make a long story short, we can address this issue by converting a non-backward compatible change into a change that is backward compatible for a certain period of time. In other words, we need to put in the extra effort and split the schema migration into two parts. Backward compatible update executed now, which usually means keeping some redundant data, non-backwards compatible update executed after the rollback period time that defines how far back we can revert our code. To illustrate this better, let's look at the following image. Let's think about an example of dropping a column. A proposed method would include two steps. 1. Stop using the column in the source code. 2. Drop the column from the database. Dropping a column was a very simple example. Let's have a look at a more difficult scenario and rename the result column in our calculator service. We present how to do this in a few steps. First, we will be adding a new column to the database. Let's say we need to rename the result column to sum. The first step is to add a new column that will be a duplicate. For this, we must create a v3_add_sum_column.sql migration file, and here we have added this code. As a result, after executing the migration, we have two columns, result and sum. The next step is to rename the column in the source code model and to use both database columns for the set and get operations. For this, we have changed the calculation class and added this code. From now on, every time we add a row into the database, the same value is written to both the result and sum columns. While reading sum, we first check if it exists in the new column, and if not, we read it from the old column. All the changes we made so far were backward compatible, so we can roll back the service anytime we want to any version we want. The last step is merging the data in both columns. This step is usually done after some time when the release is stable. We need to copy the data from the old result column into the new sum column. Let's create a migration file called v4_copy_result_into_sum_column.sql and add this code. We still have no limits for the rollback. However, if we need to deploy the version before the change in step 2, then this database migration needs to be repeated. At this point, we already have all the data in the new column, so we can start using it without the old column in the data model. In order to do this, we need to remove the code related to result in the calculation class. After this operation, we no longer use the result column in the code. Note that this operation is only backward compatible up to step 2. If we need to roll back to step 1, then we could lose the data stored after this step, so we save this file. The last step is to drop the old column from the database. This migration should be performed after the rollback period, when we are sure we won't need to roll back before step 4. Let's add the final migration, v5_drop_result_column.sql, and add this code. After this step, we finally completed the column renaming procedure. Note that all we did was complicate the operation a little bit in order to stretch it in time. This reduced the risk of backward incompatible database changes and allowed zero downtime deployments. We will now look at avoiding shared database. In many systems, we can spot the database becomes the central point that is shared between multiple services. In such a case, any update to the database becomes much more challenging because we need to coordinate it between all services. For example, imagine we develop an online shop and we have a customers table that contains the following columns: first name, last name, username, password, email, and discount. There are 3 services that are interested in the customer's data: Profile Manager, this enables editing users' data; Checkout Processor, this processes the checkout, reads username and email; Discount Manager, this analyzes the customer's orders and sets the suitable discount. They are dependent on the same database schema. Each service should have its own database, and the services should communicate via their APIs. Following our example, we could apply the following refactoring. The checkout processor should communicate with the Profile Manager's API to fetch the customer's data. The discount column should be extracted to a separate database or schema, and the discount manager should take the ownership. Such an approach is consistent with the principles of microservice architecture and should always be applied. The communication over APIs is way more flexible than the direct database access. With this, we conclude this video.